divides it by a basis of states, which are just n1, n2, dot, 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 and I, dot, dot, dot. The n's are the occupation numbers. They're the occupation numbers which tell you how many particles there are with each energy level. Okay? And those are states. They're not single particle states. They don't even belong in the same vector space with the single particle wave functions. The single particle wave functions are themselves a whole vector space. But we're now talking about a bigger thing, a bigger system, and so we should not confuse the single particle states with the more general structures that we're talking about. We use the same notation for them because nobody ever invented a better notation than the rats, bras, and cats. But okay, next we would like to be able to change the number of particles. Maybe we do or maybe we don't want to change the total number of particles. That's not clear yet. But we'd like to be able to change them, and so we'd like to be able to raise and lower the n's. So we introduce a oscillator for each I. For each I we introduce an oscillator, and at the moment this has nothing to do with oscillation. This is just a trick. This is just a bookkeeping trick, although it will be more than that later. For each one of these I's, we introduce a creation operator or a raising operator. Let's call it a creation operator since it's now going to create a particle. A creation operator and an annihilation operator. And the creation and annihilation operators, it's convenient to make them just work exactly the same way as harmonic oscillators. It's just a convenient way of dealing with them. A plus I and a minus I. Now I should tell you right now that another convention for the same things, I'll write this in red, is to call this a dagger I. That looks like a plus sign. Not quite, but nevertheless, same thing. And just calling this one AI. You'll often see it written that way. It's the same thing. A dagger creates a particle, A does not, but the correspondence is exactly this. Okay. This space of states of the many-particle system is called Fock space, F-O-C-K. Fock was a Russian physicist who somehow got his name attached to this. I don't really know how. Okay. Now we're going to find very convenient, you'll see how it works, to introduce the notion of a field operator. The field operator has the same symbol as the wave function psi of x. But it's not a wave function. It's not a wave function. It's not a state vector for one particle. It's an operator. And it's an operator that acts on the space of states of the many-particle system. It itself contains creation and annihilation operators. All right, so let's write the notion of a field operator. And the best way to motivate it is to use it and see what it does. Now I use a uppercase psi. I hope. I'm a little bit afraid that you won't be able to tell my uppercases from my lowercases. That's an uppercase psi, right? Its definition is the following. It's the sum over I of, to get it straight, the annihilation operator for a particle in state I times the wave function of a particle if it were in state I. And that's it. Summed over all I. Now somebody asked me last week, does this have anything to do with Fourier transforms? You bet it does. If the wave functions here or the wave functions of a free particle, the eigenstates of energy of a free particle, in not a box, just in an infinitely big box. What are those eigenstates? Those eigenwave functions? They're plane waves. E to the I kx and e to the minus I, or e to the I px and e to the minus I px. So in that case, if we were using free particles in an infinitely big box, this would be an expansion in sines and cosines, and those a's would be the coefficients of sines and cosines. They would be the Fourier coefficients of a Fourier expansion, except that they're not numbers. They're operators. They're operators are things that you measure, or things that play the role of operators in quantum mechanics. Okay, so that's one thing. The complex, or the Hermitian conjugate of it, so a dagger of x, this is of x. Yeah, what does it mean to say we have an operator which depends on x? Well, it just means we have a different operator at every x, that's all. We have a lot of creation and annihilation operators. Out of them, we can build a lot of independent operators. In fact, we can build an operator at each point x by combining the a's with size of x at point x. So if we do this, we make a different operator at every position. So we have an operator function of position, or operator valued function of position. Its complex, or its Hermitian conjugate, is the same thing, except creation operators here. This is a I get so used to a minus a plus times psi dagger, some psi star I of x. Now it doesn't matter. It's rather weird. There were notations. Some people use a notation where this is called psi star, and some people use the one where this is called psi, and they get all mixed up. These are definitions, and so you can do what you want, but here's the definition we use. As I said, there are two operator functions. Now, neither one of these is a Hermitian operator. Their creation operators and annihilation operators are not Hermitian. Their conjugates are each other. If you add them, you make something that's Hermitian. If you make any Hermitian operator, any operator, and add it to its Hermitian conjugate, it's Hermitian. So if we add these two, they become Hermitian, and Hermitian means observable, means something you can measure in the laboratory. So the sum of them is the thing you can measure, and the difference is the difference Hermitian. What happens if you take the difference of a number and its complex conjugate? You get something real? You get something pure imaginary. But if you multiply it by I, then you get something Hermitian. So the sum and difference of these define some Hermitian observables. But right now we're not observing them. We're just going to use them as bookkeeping devices. Okay, now let me show you another interpretation of psi of x, what it does. In particular, let's ask what it does when it acts on a vacuum. The vacuum means a state with no particles in it at all, and so the vacuum, let's call it vacuum, which we usually denote just by O, is really the Fock space state in which all the occupation numbers are zero. All the same thing. A vacuum, Fock space state in which all the occupation numbers are zero, sometimes just called the vacuum, or just called the state zero. Okay, let's act. Let's not act yet. Let's write down the following formula. This is a one-particle state panel. One particle and only one particle. And let's write it in the following form. Let's use this. Anybody know what the name for this kind of formula is? No, it's not a, well, it is a projection. It's the trivial projection operator. It's one. It's called a resolution of the identity. It's a way of writing the unit operator as a sum over a lot of orthogonal vectors. All right, so let's plug in the resolution of the identity. Sum on I, psi. What is I? I is a state in which there's one particle and only one particle in the ith energy level here. What is this thing here? This is X. X, sum of I, xi. What is this object?